Hello, everybody, and welcome to We Measure the World, a podcast produced by scientists for scientists.
Okay, we got this project. We need to measure the gas concentration in the subsurface at 50 locations. What do we have that can do it? Oh, by the way, we don't have anything. Okay, so let's try to figure out how we can match what's commercially available with some different techniques to engineer a casing and then test that in our lab, of course, before we then go deploy it into the field and try to address all of the field issues and conditions.
That's just a small taste of what we have in store for you today. We Measure the World explores interesting environmental research trends, how scientists are solving research issues, and what tools are helping them better understand measurements across the entire soil-plant atmosphere continuum. Today's guest is Dr. Kate Smits. Kate is a professor at Southern Methodist University's Lyles School of Engineering, serving as chair of the Department of Civil and Environmental Engineering and the Solomon Professor for Global Development. Prior to SMU, she was a professor at the University of Texas at Arlington and an associate professor at the Colorado School of Mines and the U.S. Air Force Academy. She earned a bachelor's degree in environmental engineering from the U.S. Air Force Academy, master's in civil engineering from the University of Texas at Austin, and doctorate in environmental science and engineering from the Colorado School of Mines. She served as a civil and environmental engineering project manager and officer in the U.S. Air Force, and her research interests are focused on energy and the environment, with applications to natural gas leakage, the cleanup of contaminated soils and waterways, and the storage of renewable energy. And today she's here to talk to us about her most recent research on natural gas leakage from pipelines. So Kate, thank you so much for being here.
Thanks, Brad. Yeah, great to be here. And thanks for the invitation.
With all of our guests, we would love to get to know you better. And would you be able to tell us a little bit about your background, how you got into sciences in general, and what brought you to, civil and environmental engineering?
Yeah, I've always really loved science and engineering since I was young. The thing that attracted me to environmental engineering is my passion for this intersection of engineering solutions to environmental problems. And most environmental problems also involve the complexity of humanity. And I love working at that intersection between environmental issues that involve both science and engineering and this whole human aspect to it as well. And so that's always really, really motivated me. And I've always wanted to work in that area in my career.
Was there a specific trigger during your education where you said, yes, this is the path? I was thinking about some other things, but I want to go down this road now.
Yeah. So when I was an undergrad student, I was at the U.S. Air Force Academy, and I actually wanted to major in aerospace engineering, is where I really, really thought I was passionate about. But I met a professor when I was there. Guy's name is Rod Jenkins. He's retired now. And I found his work so interesting and motivating because with environmental engineering, we study lots of issues. So not only the traditional aspects of environmental engineering, a lot of folks see us as either landfills or sanitation engineering. And that, of course, if we go back 50 years, was the foundation of it. But his work was really pulling in energy issues and sustainability issues. And I found that really fascinating and motivating to major in that field. But in terms of research, I didn't get interested in research until I was back teaching at the Air Force Academy. So I had a master's degree. I was still on active duty in the Air Force, and went back to the academy to teach. And one of my advisors that was there, John Christ, who's also an environmental engineer, he started introducing me to a couple of different papers that he had been working on in the biological field that was on environmental remediation using a specific organism that was D. helicocoides. And I started reading these papers and started noticing the holes in the research, as I like to call it. The holes or the gaps in the knowledge. And it was really the first time that I ever acknowledged that I was going, oh, I can see where there needs to be additional research or an improvement. And that was the first time working with him that I was able to experience that and go, oh, I think that's really fascinating. I'm curious about these gaps. And I have ideas on how to fill those gaps and how to address some of the questions that arise. Because before that, I never understood how to do research or how to come up with a question that was even novel. I always thought that's for really smart people, not necessarily for me, and didn't have that level of confidence yet. But that's one of the things that really drove me into wanting to stay in academia and be a professor and work with students and help them to find that pathway with research. So I find that very motivational to be a faculty member, and my favorite part is getting to work with students. We mess up the whole faculty positions with all the admin crap that we end up doing, but but in general, the teaching, and especially the teaching of graduate students through that mentoring with research, I find absolutely wonderful.
You talked about some of the beginnings of environmental engineering. Could you back up and kind of give us a quick overview of that discipline and its overlap with and distinction from, civil engineering and environmental science?
Yeah, absolutely. And this is Kate's version of it. So I'm sure there's a more technical version of it, but environmental engineering really stemmed out of civil engineering, where we had sanitation engineering, so treating water and wastewater, and then landfill trash management. And that held with the major for a long time. And the thing that then made it, I think, break off from just being part of civil engineering is what you're getting at, Brad, is this intersection with environmental science. Because with environmental engineering, it's really this bringing together of an understanding of chemistry and biology and physics, as well as the whole engineering process and mindset, and how to integrate that around issues that have to do with the environment and making engineering processes better and more sustainable and more environmentally focused initiatives. Today, I think environmental engineering is really moving more forward with the integration of sustainability and big focus on energy and energy issues that we have. And that includes traditional energy issues as well as renewables. And so it's a neat place to be and see how the degree and then the different career options have branched into a lot of different areas over the years. But yeah, but I think it's a great degree for students who are interested in this intersection of trying to solve engineering problems, but doing that with an environmental focus and an environmental motivation and mindset.
Right, right. I was also checking on your LinkedIn bio, and you mentioned there that you're looking into the development of socio-technical systems and creating models to better understand those. That caught my attention. Can you tell us a little bit about what you mean by social or socio-technical systems?
Yeah, we could go on down a rabbit hole on this one for for a long time. But to give you the skinny on it, a lot of times as engineers, we look at any sort of problem as it has an engineering solution to it. And that can work. And a lot of folks that go into engineering are motivated by those engineering solutions. However, as engineers, everything that we engineer has a human behind it and has a huge social component to it. And so, what my work really looks at is how we can integrate both of those, not just look at them individually, because I think a lot of the work in the past with engineering and with social issues has been parallel as opposed to integrated efforts, but really looking at how we can address an issue from both the social components and looking at all of the human aspects behind it and integrating that with an engineering solution, I think is critical for us going forward. And there's so many examples out there of engineering solutions that have failed. And the number one reason why they fail is because they don't consider integrated stance or integrated component, that social component. And, maybe but we went and we talked to a couple of stakeholders, or we did a survey. As engineers, we like to say, oh, that checked the box in terms of considering the social component. But what we know is that it doesn't. And we need to go a lot deeper into the understanding of why people do things, why their system is the way it is. Maybe the folks that we're trying to design something for already have the solution, but oh, by the way, we failed to ask what that solution set is because we thought we knew better, or we had this fancy education. And how could they know the solution? We're just going to take our engineering hammer and put it behind it. So a lot of my work integrates those components into the overall solution set.
So it really is a kind of a interdisciplinary, or at least it could be or should be interdisciplinary between, engineering, environmental science, even getting to sociology, organizational behavior, all that kind of fun stuff.
Absolutely. I work with anthropologists and, just like you said, engineers and scientists, and, to truly integrate those on equal playing fields within the solution set, as opposed to seeing certain things as an afterthought.
You've done a lot of work and we mentioned this in your bio, your research interests are varied when it comes to environmental engineering. And one of your more recent projects deals with natural gas leakage from pipelines. And I think this is interesting just because here on the podcast, we've talked a lot about soil scientists, or we've talked with soil scientists, and we've talked a lot about water movement through soil or nutrient transport. But this is the first time I think that we get to touch on and discuss gas movement within the soil. So I'm super excited to talk about this project. And I just want to know, just as a background, how did getting into natural gas, how did this come about? What is the background of it? What are the objectives? Can you just kind of give us a little bit of insight into how all this got started?
Yeah, absolutely. So my PhD work was on multi-phase flow and transport through porous media, and it was sponsored by the Department of the Army, by ERDIC, the Engineering Research and Development Center. And we were looking at landmine detection, and how, if we can better understand the environmental conditions in which landmines are placed, we can work that understanding into the algorithms that the Army's using to detect the mines. So, to give you a simplified example, to detect landmines, operators can use ground penetrating radar, they can use thermal imagery, they can use some sort of gas sensing. And what normally happens is they'll use multiple technologies in unison, and then, for a lack of a better word, triangulate the data. Right. So if you have some understanding of a moisture difference, if you have some understanding of a temperature difference, and maybe you have some sort of gas sensor, when you look at all of this information together, you can then better understand, do I have a buried object that I want to respond to? Or do I have something that's maybe a buried rock or a buried soda can? And so what we were working with the Army is, if we can take the understanding of the environmental conditions, work that information into their algorithms that they're using to detect the mines, they'll have less false positives, spend less time, manpower, money digging up stuff that is not actually there. And so through that experience with my PhD, I had the opportunity to look at that both through experimentation and then through mathematical modeling. And so with the experimentation, we were measuring moisture content, like you mentioned, Brad. We were measuring temperature, thermal properties of the soils, and then really getting into differences in surface properties and how that was impacted by changes in weather conditions, and trying to integrate all this information. And what that really led me to question or try to understand better is the gas itself. So if we have these buried objects that are made up of explosives, over time, the gas is going to start to come out of these buried objects, and it's going to move through the subsurface, through a very tortuous pathway because of the soil, because of the differences in soil type, because of the moisture that's involved that's creating these tortuous pathways. And those gas molecules are eventually going to get to the surface, and then they're going to exchange with the atmosphere. And maybe there's an opportunity to be able to use gas sensing more intentionally to detect the mines, both in the atmosphere, on the surface, or even below the ground. So if we had some sort of device that we could do that, then we could better understand the detection of the landmines. And so that then got me questioning quite a bit of where is the gas going and how is the subsurface impacting that gas transport. How is the differences in the surface type, and whether that be a grass condition or a sand condition, pavement, etc., how is that impacting the exchange processes between the soil and the atmosphere? And then after those gas molecules get into the air, how are the changes in the weather conditions really impacting where that molecule goes? And of course, when we're talking about measurement, if we're trying to measure something below the ground, it's going to be a different approach and at different concentrations than if we're trying to measure it on the surface or if we're trying to measure it in the atmosphere. So all of that understanding of the flow and transport from a gas perspective then got me linked up with the questions of natural gas leakage from pipelines. So the work there actually started through a couple of projects that were sponsored by the Department of Energy. So I'm going back over a decade now, when I was an assistant professor and then an associate professor. And so I paired with a researcher at Colorado State University, Dan Zimmerly, on a Department of Energy project and did a small portion of a huge effort. So we're talking, 100K portion of a multi-million-dollar project to try to understand leak detection linked with natural gas leakage from below ground environments. And to make a long story short, we did a great job. My students and I did a great job on this effort that it really then started growing legs, as I like to say. And that research project then led to another research project sponsored by the Department of Energy's ARPA-E, which then led to research that I do now through the Department of Transportation's Pipeline and Hazardous Materials Association, as well as some Colorado groups and industry groups on natural gas leak detection. And so my interests now are multi-phased, right? So it's on the behavior of the gas in the subsurface, how that's impacted by both operating conditions as well as the soil and transportation conditions, and then how we can use that understanding of that transport both below ground and above ground and integrate that into our leak detection technologies that we're using to mitigate gas leakage and therefore its occurrence and its consequences. My interest specific to pipelines is because of the vast network of pipelines we have in the United States. There's over 2 million miles of natural gas pipelines throughout the United States. And so this includes all the way from the source, so our gathering lines, all the way to the customer and these distribution lines and the transportation lines in between. And there is a great need to be able to understand the leaks from these pipelines and how to find them and fix them. So ultimately, my goal is to be out of a job once we figure out how to find these leaks effectively and fix them, and do that efficiently so that I can move on to other topics. So, yeah.
With the pipelines that you're working with, you talked about the distribution, the gathering distribution lines, and this is all compressed natural gas. Is that correct? I mean, I guess we're not dealing with like liquefied gas. That would be for large transport and
Right.
other things like that,
Yep.
right? All right. So we're dealing with compressed gas, natural gas. Again, for those in our audience who may not know, that we're dealing with methane, colorless, odorless, a huge greenhouse gas when it comes to efficiently trapping heat.
Right.
But so very important to be able to transport this safely. And as we've seen, unfortunately, it's highly flammable. So there's definitely lots of potential issues when it comes to how best to manage natural gas and its flow and transport and all of that. I'm super interested in your project setup and because you guys got to build stuff and test things out. That I guess from the stuff that we've seen previously with other environmental scientists and soil scientists and others, a lot of times they don't get to build stuff to test things out. And so, can you tell us a little bit about your about that setup that you had going on?
Yeah, absolutely. So, the best part of my job, besides working with students, is getting to be creative in the lab and in the field with experiments. What we typically do is try to measure things in new ways that haven't really been done before. So, we oftentimes have to take commercially available systems and then modify them, sometimes a little bit, sometimes a lot, to meet our purposes. And that's because of two reasons. Number one, because we're poor academics and don't have the funding to go buy fancy dancy equipment for everything. And so we want to be able to kind of build it ourselves is what ends up happening. And number two, because maybe there's not something that's commercially available. So there's part of it that is, but we need to modify it in some way. So I'll give a couple of examples of that. So, most recently, with my work with natural gas and pipeline leakage, I've built test site in collaboration with Colorado State University and specifically with Dan Zimmerle's research group at the Methane Emission Technology Evaluation Center. So it's called METAC. And as part of METAC, we have a pipeline test bed. And so the pipeline test bed consists of about 50 below ground controlled leak locations that will simulate different size and type of leaks from the subsurface. And so what this allows us to do, which is what we cannot do in the field, in a normal field environment, is to know the ground source, as I call it. So we know the actual size and type and composition and location of the leak. And if we know that information, we can then ask and address a whole variety of questions around it. And so that's what we've been doing with this test site. So the test site's set up, if you can imagine, about an 8-acre site that has, like I mentioned, these 50 below ground leak sites that we can turn on and turn off. And we can do that from really small leaks to really big leaks. So from for leak people out there, it can go anywhere from about 1 standard liter per minute all the way up to about 200 standard liters per minute. So that's about 2 to 400 standard cubic feet per hour. So that's a tiny leak that you would see in a distribution system, all the way to a really big dozer of a leak that would make the front page of the morning news. And then, so what we do is then instrument the subsurface, the surface, and the atmosphere with a wide variety of sensors so that we can continuously monitor the soil moisture. So, in terms of the soil properties, we're interested in the soil moisture and pressure and temperature. And then from a weather perspective, we're interested in measuring all of our weather variables. So we use, for example, the Atmos 41 that y'all have. I think it measures like 12 weather variables. So we have those set up all over the site. Then we measure our subsurface natural gas concentration. So we're actually measuring methane and ethane below the ground. And so we do that at anywhere from 2 locations up to about 50 locations at a time below the ground. And then we do that on the surface. And then we also have atmospheric sensors that are measuring the methane concentration and the ethane concentration. And so when we're measuring the subsurface gas concentration, if you can imagine a gas leak and putting sensors in the ground, the concentrations are going to be much, much higher than the concentrations once that gas gets into the atmosphere. So the sensors we're using for atmospheric measurements are trace gas sensors. So this is at like the part per billion range. But when we're trying to measure below ground gas concentrations or surface gas concentrations, we can measure in the parts per million range. And so we're able to use a sensor that is less accurate, has less sensitivity, is, oh, by the way, a lot cheaper. But we can then do so at a higher space and time, a higher spatial and temporal resolution than we can in the atmosphere. If we're using a trace sensor in the atmosphere, that sensor is going to work amazingly for trace gas concentrations. But if we take that same sensor and stick it below ground, it's going to come unglued because the concentrations are too high. So it's very important to match the sensor with what we're trying to measure. So the sensors that we use for measuring methane below ground, it's a INIR sensor. So it's an IR absorption sensor that's commercially available. And I think it's made by SGX or something. Anyway, that sensor is normally used in some sort of, it's not a fire alarm, but some sort of emergency alarm system. And what we did with the sensor is we created a new casing for it so that it would not be affected by the subsurface conditions, because in the subsurface we have really high humidity. Even if the moisture's low, the humidity is still really high. And then, oh, by the way, we often have high moisture. And so we needed to be able to have a sensor that could operate in that environment, but do so within the range of concentrations we were trying to measure. And so, to be able to do that was a lot of fun, because I always call it a pre-project to a project. So, okay, we got this project. We need to measure the gas concentration in the subsurface at 50 locations. What do we have that can do it? Oh, by the way, we don't have anything. Okay, so let's try to figure out how we can match what's commercially available with some different techniques to engineer a casing, and then test that in our lab, of course, before we then go deploy it into the field and try to address all of the field issues and conditions. And so we're real successful about being able to do that with our subsurface sensors. Did the same thing with a surface sensor, but with a different type of sensor. We're using a catalytic oxidation sensor for our surface and our below ground near surface measurements, and then trace gas analyzers for our atmospheric measurements. So I think what makes our experimental setups really unique is that we're able to measure the entire continuum for gases. So both in the surface, on the surface, and in the atmosphere, and then link that with all of this weather and soil data so that we have this complete picture of what's going on in the environment. So it creates these massive data sets that are also very powerful, because it takes away a lot of the ambiguity in, oh, well, we're going to blame it on on one process, one physics process versus another. We can actually measure it and then understand the whole picture.
With a lot of these measurements, are you testing these out in the lab as well as the fields? But are you comparing lab results versus field results with these measurements?
Yeah, we do a lot of calibration and validation in the lab. So in my lab, I have soil tanks that are various sizes. Some are, the size of a fish aquarium that you'd have in your house, all the way up to some larger ones that are maybe about the size of a car. And we instrument them with these same sensors and run pilot scale tests in the laboratory. Other times we run smaller stuff where it would just be, we use the term a Tempe cell scale size. So just the size of a large coffee mug that we instrument with one sensor and then run gas through it, change the soil moisture. We have a controlled temperature room in my lab where we can make it really cold or really hot and change that condition, and then test out how our sensors are operating. What I've really learned over the years, and I'm sure Brad working at Meter, you can resonate with this, is that it's really easy to get average data. Really easy that you can just, okay, I can read a user manual, I can plug in a sensor and I can get data. What's really the whole, as I tell my students, the devil's in the details. What's really difficult is to get scientifically repeatable and verifiable data that you really trust. And that involves a lot of steps to go through so that we can weed out, where the problem is in the data set or in the operation or in the person that is operating the sensor in order to get data that we trust. And so when we go to the field and we're trying to measure the whole soil atmospheric continuum continuously at high space and time resolutions, we need to be able to do that and have all sensors operating in unison together. So we do a lot of practice like we're going to play in the lab to figure out how this is all working before we go and do that in the field. And, even after, trying to do this multiple years, we still, every time we have a field experiment, we have hiccups.
There's always something.
But
Yeah.
yeah, there is. Yeah. But the goal is to have that backup, right? And the duplicate, if not the triplicate, so we can ensure we at least get the data that we need. Because that's always the question. Okay, what's kind of the most amazing data set that we could get? And then what's the bare minimum that we need? So if we're not at least going to get that bare minimum, then it's not worth running the experiment.
Right. Tangential question, but I think it's related. What is your preference, lab or field work?
Yeah. So I started in the lab and was trained by lab scientists. And I think that gave me a level of detail that I bring to the field that perhaps some field scientists don't necessarily have. Because they started in the field, so I'm very thankful that I was able to start at the lab. My preference is looking at field scale issues, and it seems as I progress in my career, I keep getting bigger and bigger, going from just maybe a plot scale to an area to a basin to a region. And I think depending on the question that we have, we need to scale the experiment to the question. It's just my questions have evolved and changed to looking at, okay, how do we understand how to quantify emissions from a single leak versus how do we understand what our emissions are at a basin or at a regional scale so we can work that into an EPA inventory of greenhouse gas emissions. Those are two totally different questions that involve two totally different experiments. Both have absolute validity and both need to be addressed. It's just how we would address them would be different. But at this point in my career, I enjoy being in the field, but it clearly has different challenges associated with it, especially working in oil and gas fields. And, for example, down here in Texas, going out to the Permian Basin in West Texas in July is not for the faint of heart. So I always tell my students it's more than just sunscreen and bug spray. You need to be in shape to be out there and withstand that heat for working in the field for a few days.
Yeah.
So
yeah. No, I always liked having that balance as well. Like, yeah, you're in the lab, stuck in the lab for a while, and you're like, man, I need to get out. And then you get to go out and do field work, and you're like out there for a while, like, okay, I'm done. I can go back inside. Let's go find some air conditioning. So it's good to have that balance.
Absolutely. Yeah. I think, I talk to a lot of students and they're so well motivated and minded of they are interested in environmental work because they want to be in the field. And I would just encourage students, even if you're working in the lab and you just have this heart and desire to be in the field, know that everything that you're learning at that smaller scale, at the REV scale or at the pilot scale in the lab will do you wonders when you finally do get to the field and vice versa. So I think that there's benefits to both. And I think the folks, and this is, again, I could talk about this forever, but folks at various scales, we don't communicate with each other enough. So we have all these interesting findings at the pore scale, that very often don't get translated to that representative elementary volume scale, that don't get then properly translated to that field scale, because I think we undervalue the bridges and the intersections between them. And that's due to how many issues, but in part to how we're funded for our research, right? And that doesn't then value that linkage part.
So with all of this set up at your test site, and you said that you've tested things out, these various leaks in different situations, different environmental factors in play. What were some of the results then? What were the findings that you came across? What did you learn?
Yeah, absolutely. So, most recently, we were looking at the impact of different surface conditions on the gas transport below ground. And what we were really able to show with that work was the relative difference in the distance that the gas was moving and the time that it was moving when we had different surface treatments. So, to give you an example, if we just had a leak that was in a grassy field and then take that same leak and put it under pavement, and as a result, that the impact of just that one change in the surface condition. So if you can imagine a leak being under a driveway, for example, compared to the leak being under, in someone's front yard, just in their grass, the impact is an 8 times further and about a 4 times faster gas movement in that paved environment compared to the unpaved environment. And so by having this ability to run these tests very systematically, we're able to put values behind ideas that maybe fundamentally we already knew that. Okay, you take a pavement, you put a cap on the ground. Of course, it's going to make the gas move faster underneath the ground because it can't get out. Everybody knows that. It's the duh kind of kind of factor. But the point being is what we didn't know before was by how much and what the timing was, the timing associated with that. And so those are two very interesting findings to first responders and to operators who are trying to prioritize fixing a leak. And so, from a first response perspective, the reason that finding has a lot of impact is because if a first responder, so I'm talking about a fire group or hazmat group, comes to a site, they don't know what's going on underground. They have some sort of optical imagery sensor or some above ground sensor that they're just measuring concentrations in the air or perhaps on the surface, but they have no indication of the spread of the gas below ground. And so this gives some indication of that spread. From a repair perspective, that helps operators to potentially prioritize repair. So if we have a leak that is in, and I'm just keeping it simple with pavement versus we looked at many conditions versus grass, but it helps with the prioritization of repair based on the spread and the timing of that leak. What we also looked at was transient conditions. So, in the case, maybe we have a snowpack that occurs. So, maybe there's a known leak, and that leak, that then there's a snow condition that's then impacting the escape of the gas from the subsurface. That snow condition then turns into a melting snow condition, which would be similar to an infiltration front of water that's going through the subsurface and perhaps compressing the area that's available for the gas transport, that's then pushing the gas out and pushing the gas downwards. And what we were able to do with this work is to actually quantify that with how far and how fast the gas would travel when we have these changes in our environmental conditions. And so the way we translate that to practice is a couple of ways. So yes, we go write our fancy journal article papers that maybe someone does or doesn't read, depending on who you are. But in terms of operators, they don't read our fancy journal article papers, no matter what the impact factor is, because they probably don't even have access to them. And we write them in such a way that, only if you have a PhD in the area, you can really even read them, right? And so what we do to translate that science understanding into impact and into operator or first responder practice is creating things like reference manuals, by creating PowerPoint presentations that we then publicly have available that first responders can work into their hazmat training, for example. We translate that through, at CSU's METech, we call research alerts. So this is just, again, a publicly available, hey, we ran these experiments, we found this information, and I'm going to try to explain it to you in a simplified way so that we can have that connection to either industry or operator practice. Or also, I failed to mention folks that are doing the leak detection. So the solution providers, and how they can work that knowledge into their practices as well. And this is just giving one example of some of our findings, but I really want to highlight how what we're trying to do is not just have this science finding, but how can we then take that and work that into practice by partnering with industry and partnering with our first responders to make it meaningful to them. And again, talking about something that's undervalued in the research world, it's that translation of the impact to different communities, because that's a hard thing to do, because we have to, you know, try to explain something, and then whoever we're explaining it to has to go, well, that either makes sense or it doesn't make sense. And how can we have that conversation and make it something that's usable versus something that, oh, well, that's just a science finding and I'm not sure how to implement it. So it involves knowing thy user, knowing the practice, which takes a lot of effort.
Yeah, yeah. I was going to say, do you have any lessons that you might be able to share with folks? A lot of our audience are scientists, and there's always issues in being able to communicate to various stakeholders. Like you said, you can communicate within the academy. You can have your papers and articles that can be very dense. But on the other hand, there's often times when scientists need to and researchers need to communicate with the lay public. And so, yeah, do you have any thoughts or lessons on things that you have either found successful or found success in, or otherwise?
Yeah, the one that comes to mind is one of my students, recent student. He's a master's student, and when he started, the first thing that I put him on was a review of what I call gray literature. And gray literature is not the published peer-reviewed journals, but this is things like YouTube videos and websites and chat rooms and such. And it was really a review of the gray literature on leak detection and quantification methods for pipeline scenarios, specific to pipeline scenarios. And I said, there's papers out there. I want you to put those aside for a while and really just focus on the gray literature and the understanding. And he did this for about a month. And then after looking at that, I have my students give short presentations, short summary presentations on the bottom line of what they're finding. And, it's really interesting that he was already identifying, just after a month, some major holes. I said, well, what do you think you need to do to fill those holes? And he said, well, I need to talk to operators. I said, okay, I'm going to open up my Rolodex for you. You better not mess this up. And here's a handful of operators that I want you to go interview and talk to about their experiences. But first, go figure out how to frame the questions properly and how to do that interview process, right? So he spent a good month putting together these questions, reviewing them with myself and a couple other colleagues, to the point that he was then available to be a good interactive interviewer, right? Which is an art form, as you, I'm sure, know
Definitely is.
yeah,
Yes,
from
still
your
learning.
job.
Yeah.
Exactly. And through this process, he was really able to, number one, build a network of industry folks, of first responders, of solution providers that he has then used for his entire master's degree. This would be the same way for a PhD student, right? But then also just have that knowledge of what am I really trying to solve? It's one thing to say, oh, methane emissions, and I want to decrease greenhouse gases. So yes, that's important. But what is the actual thing that you're trying to solve, and who's the person on the other end of it? And I think having us identify those things at the really early stage of the research is absolutely critical. And it takes getting off of just the typical pathway of I'm going to spend all my time, running this mathematical model or designing an experiment, both of which are extremely important. But it's taking a step back and saying, let me truly understand the problem before I try to find a solution set to it. And so I think that problem identification with the people who are experiencing the problem is key. So any way to really get into the actual practice of where the problem is and embedding ourselves in that for a period of time is critical. And the student I was talking about, his name's Richie. He was great. He got to the point where he was developing his own relationships with these industry operators, and was then going on leak detection survey operations because he goes, well, I need to see what they're actually doing in the field, and taking 3 or 4 days to go do that, and walk around or drive around with folks or fly UAVs and understand their opportunities as well as their limitations with their practice. So I think that is ultimately the key, is finding the way into understanding the true problem through integrating ourselves into it, going all in.
You'd mentioned modeling, and I know that modeling is part of this project as well. And as you create, I guess, predictive models from your findings, what would be some of those key parameters that would be the main, I guess, the main drivers for gas flow within the soil?
Yeah, yeah. The models, we use different types of models, and again, just like with an experiment, it's matching the model to the question. So one model does not work for all sizes and shape of research. But when we're looking at gas movement through the soil, it's caused by four main different things. So it's caused by the gas moves due to a concentration gradient. So this is your diffusion through the soil. It moves due to a gradient in temperature. So that would be your convection. Density differences. So these buoyancy effects. And then pressure differences that we often call advection through the soil. And so when we have a leak from a pipeline really close to the leak itself, the main driver of the gas movement is due to the pressure differences. So that advective transport. But then as we move away from the leak, the concentration gradient takes over. So we have more of a concentration, this diffusion effect as we move away from the actual leak location. And then, of course, throughout we have these gradients in temperature. And that is more influenced when we're close to the surface and due to the diurnal changes in the in temperature. And then density. Well, methane is a light gas, and so of course buoyancy will come into play there, depending on the amount of methane versus other components that we have in the natural gas mixture. And so, with our work, one thing that we have focused a lot on is that diffusion effect. Another finding that we had that was really interesting, that we were able to show first through our experimentation, but then really confirm with our validated numerical models that were validated based on all of this experimentation, is the impact of the diffusion on the gas transport. Because that's a major one when we're talking about especially these low level leaks that persist for long periods of time. And so you get this diffusion transport, this diffusivity that occurs over time. And even if that leak is turned off, you are fixed. If you think about the outer edge of a gas plume, because you still have a concentration gradient on that outer edge, you still are going to get diffusion. So you're still going to get transport away from the actual leak location. And that was another interesting point that industry hadn't necessarily considered in all of their practices. That, okay, normally we fix the leak, and the leak should eventually, the gas should clear up in the subsurface, and it does over time depending on the conditions. But that outer boundary of the leak, what we were really able to show, can continue to creep out about 3 to 4% for just your average leak situation that's underneath some sort of surface barrier. And so, that 3 or 4% difference in distance may or may not be important depending on the leak scenario that's occurring.
So I know we've got a lot of soil scientists around here, and they would get upset with me if I didn't ask about how the soil and soil characteristics affected that flow of gas, whether it's permeability of the soil or soil moisture or other characteristics.
Yeah, permeability is a big one with our gas transport. So when we have a highly permeable soil, the gas is going to move quicker through it than a low permeability soil. The thing that's interesting to me, and this may sound stupid, but yeah, your soil scientists are going to be laughing, is when I talk to the lay public, they get porosity and permeability mixed up a lot. You can have a soil that has a high porosity but a low permeability, is a concept that just I never realized, because of my background and training as well, that would be something that folks wouldn't quite understand. So you take clay, for example. Clay has a really high porosity to it, but it has a really low permeability. So what happens is the gas gets trapped in the clay, and a lot of it, because there's a lot of pore space that's available for that gas to go. And so this is an issue in the field. I'll just give you an example down here in Texas, where we have a lot of clay soils. And there was an incident, I think it was back in 2019 in Georgetown, Texas, where they had to shut down a huge area of Georgetown, Texas. I don't know what the total area is off the top of my head, but it was for a long period of time, months, and it was both housing and industry areas, so it's commercial areas with a gas station and a dry cleaner and restaurants, etc., because of natural gas that had gotten into the clay and they couldn't get it out. And that's because of that permeability issue. So, yeah, it got in there, and a whole bunch of it got in there, but they couldn't get the concentrations below the proper safety levels. Just like you were saying, Brad, that natural gas is highly explosive. Methane's lower explosive limit's 5%, and then the upper explosive limit, I think, is 11%. So you have this range where we really have a problem. And so, of course, those values for operators are even lower, that they're concerned with concentrations, and they couldn't get the gas removed from the subsurface due to this high porosity but low permeability soil. So this is something that we consider in our models. This is something that we consider in our experimentation, is looking at different soil types, looking at different soil layering. Because in a lot of cases, we may have a sand soil, for example, that's then overlain by a clay soil that maybe you then have some sort of topsoil situation. And so looking at how we can incorporate different soil layers, soil textures, and then, of course, different soil moistures into our understanding when we do our experiments. One thing we then go try to back out from a field perspective, how do operators look at soil and soil types? And just, I've never done an actual survey on it, but just asking people of, just go ask your kids, right? Of what are the different types of soil that exist? And, they'll say, well, there's a clay, there's a sand, and there's something else maybe. And in general, even if you ask very educated people, that's kind of how they view soil, right? As soil scientists, we love to look at the whole spectrum of soils and all the little idiosyncrasies in each one that then impact the physical and thermal properties of the soil and hydraulic properties. But the rest of the world views soil, I think, in these larger categories, and how we can integrate that understanding with what we're seeing with our experimentation and numerical modeling is, again, always a challenge.
So from here on out, What are the applications elsewhere? What can you take and share with stakeholders or others when it comes to helping improve, I guess, mitigation, prevention, even getting into regulation or policy frameworks? What are the next steps there? And I guess what are the implications of what you're finding here?
Yeah, that's a great question. So what we're really showing is that the environmental conditions have a big effect on where the gas is going, both below ground and after that gas escapes into the atmosphere. And this information then impacts number one, the first responder response, but then number two, the leak detection and specifically your chance or your probability of detecting the leak. And what we've been looking at most recently through a project that's sponsored by the Department of Transportation's PHMSA is how weather conditions and subsurface conditions affect the detection probability, and looking at that for all of the different mobile survey applications. So to detect a leak, operators use one of a wide variety of leak detection methods. So, the most traditional one is doing a walking survey where you're taking a sensor and walking along a pipeline extent. Another one is driving along that same pipeline extent using a mobile operation, so a vehicle with sensors mounted on the vehicle. There's also UAVs or fixed winged aircraft, and then more recently using satellites to try to detect leakage. And so, what we've really been showing is first and foremost, pipeline leaks are different than above ground leaks. So, if you have a below ground leak, and this can be a pipeline or it could be a well or anything, it could be, we could talk about carbon sequestration sites, we could talk about a hydrogen pipeline or a carbon dioxide pipeline. Because of the subsurface environment, that's going to impact the development of the gas plume, the surface presentation of that plume, and therefore the exchange with the atmosphere. And so none of that, to my understanding, is currently being incorporated into our leak detection protocols, where the leak detection community has developed based on above ground leak scenarios. So we're talking about leakage from infrastructure on well pads or I don't even know what the above ground stuff is called, but the same solution set can't be translated to below ground leak scenarios. And we've really been showing that and the impact of the diverse environmental conditions on the detection probability. And so just to give you a very simple example, we know if it's raining, you're going to have a less of a chance of detecting a below ground leak than when it's not raining. The question is by how much? And we can also say that about about the wind conditions, about the atmospheric stability. Then we can link in the operator practice. So what if we're walking or driving or flying a UAV over a pipeline extent versus being, I don't know, 5 feet off of the pipeline extent? How's that impacting our detection probability? Or if we have our sensor that is mounted at a certain location on our mobility unit, on our vehicle, or if we're changing the speed of our leak detection operation. And how can we pull all of these different variations in both our practice as well as the environmental condition into an understanding of how to better detect leaks? And so we've really been trying to pull that together. From a policy perspective, most recently there's been some draft regulations that have come out through the Department of Transportation's PHMSA and then through the Environmental Protection Agency on leak detection. And our work is really foundational from a science perspective to those regulations when we're looking at trying to define what sensor minimum detection limits are needed and how we can properly define that. We may need a different minimum detection limit from an above ground leak than a below ground leak, but we don't know that unless we do the science behind it. More recently, there's been a focus with the EPA on measuring emissions from natural gas infrastructure. And so in the past, that's been done through a process called emission factors. And we need to get more science and, testing into the development of those emission factors that then can serve as a foundation to part of the regulation. That happens piecemeal, as we all know, in our system. And I think the more that we as scientists can think about how our own work translates to policy, or how we can do work that could potentially inform policy through that science foundation and understanding, I think is really important.
So that leads into then my final question about the future of this research. What do you see going forward in the next 5-10 years or so? Are there any emerging technologies that you'd love to get your hands on? I mean, you talked about UAVs and satellites. What do you think is in store for this kind of research?
Yeah, I think really looking at the understanding between these, we call them bottom up versus top down inventories of greenhouse gas emissions, is an interesting space. When I talk to solution providers, there is a lot of disconnect between an understanding of what we're measuring, what we think we're measuring, and what we're actually measuring. And a lot of that is because of a lack of validated testing. So controlled testing, where, as I mentioned before, we know the ground truth, and we can run either the same test over again, or look at the impact of changing just one variable on our outcome. And I really think that we need to do that more. I think we need to do that at a larger scale. The issue with that is that the solution set is not always the same for all leak scenarios. The other thing that I think we need to be looking at from a sensor perspective is how to measure leakage, both the existence of a leak and then the amount of the leakage. So, the concentration and the volume, especially in light of carbon sequestration. And, we talk a lot about using the subsurface to store stuff, but we don't think a lot about, well, how do we know that that's actually working? And it's to me, it's a bit of the cart before the horse. And we really need to think about what it is that we're doing and how we're ensuring both the safety and the environmental concerns that are associated with that. So I think that there's a lot of interesting questions in that space as well.
Any final thoughts? Anything else you'd like to share before we wrap things up?
No, I think your questions were fantastic, and appreciate the opportunity to share some of my research. So always love talking about research opportunities, and especially with you all. So using a lot of your moisture sensors and atmospheric sensors over the years. So appreciate that.
Oh, good. Well, thank you. We appreciate you coming on, Kate. Thank you again. Our time's up. Yeah, it's been a really interesting conversation. Again, like I said, this has been the first time that we've really been able to talk about gas exchange and transport within the soil. So it's been really enlightening. It's been fun.
Thanks, Brad. Appreciate it.
And if you in the audience have any questions about this topic or want to hear more, feel free to contact us at metergroup.com or reach out to us on Twitter at meter_ENV. And you can also view the full transcript from today in the podcast description. That's all for now. Stay safe, and we'll catch you next time on We Measure the World.